Hey everyone, let's dive right into today's explainer, the widest binary tree level problem. You know, trees can feel a bit chaotic to navigate compared to simple linear lists, but today we're going to shift our perspective and unlock a remarkably elegant solution to this classic coding interview question. First things first, what exactly do we mean by width here? It's not as straightforward as just counting the visible objects on a shelf. The problem asks for the distance between the leftmost and rightmost non-null nodes in a specific level. And here's the catch, the real trap. We actually have to count the phantom empty space between them too. Let's look at how this plays out on the bottommost level of a tree. Say on the far left, we've got a node with a value 8. On the far right, a node with the value 14. If we just went ahead and counted the actual nodes in between, the 8, 9, 11, and 14, we'd probably think the width is 4. But remember our definition. We have to include all those invisible null nodes between that 8 and that 14. When we count the real nodes plus those empty placeholders, it gives us a true level width of 7. So the illusion we're dealing with becomes incredibly clear as we scan down from top to bottom. The number of physical nodes in a level almost never equals the true width of that level. On the second level, sure, the width is 2 and the node count is 2. But by the third level, we have a width of 4 with only 3 actual nodes. And again, on that bottom level, a width of 7 with only 4 actual nodes. We absolutely need a systematic way to measure this distance without getting tricked by the missing pieces. To crack this, think about a data structure you use all the time, an array. Determining distance there is an absolute breeze. You just look at the indexes and subtract one from the other. It's simple arithmetic. You don't even have to think about it. But trees? Well, trees don't natively hand us these neat sequential indexes, and those hidden null nodes make it basically impossible to just count our way across without losing our minds. So here is the million-dollar question. How can we bridge that gap? What if our binary tree did have indexes? If we could somehow assign mathematical indexes to our tree so it behaves exactly like an array, we could completely bypass the hidden null node problem. We wouldn't need to physically traverse every empty space. We'd just look at the index of the first node, the index of the last node, and do some basic math. Let's see how this works in practice. By giving the root node an index of 0, we can systematically, mathematically, assign an index to every single node below it. And the absolute best part? This mapping naturally accounts for the null spaces. Even the missing nodes get a hypothetical index. This means our physical, non-null nodes perfectly align with their true spatial position on the level. The formula to pull this off is elegantly simple. You don't need a degree in advanced calculus here. It's a wonderfully direct relationship. For any node sitting at index I, its left child will automatically sit at index 2 times I plus 1. Its right child? That sits at index 2 times I plus 2. So if your parent is at index 2, the left child is at 5, and the right child is at 6. It perfectly preserves the spatial structure of a binary tree, branch by branch. With those indexes successfully in place, this complex, messy tree problem literally collapses into middle school math. To find the width of any level, we just take the index of the rightmost non-null node, subtract the index of the leftmost non-null node, and add 1. Just like that, boom! Those confusing null nodes are entirely factored into the calculation without us ever having to explicitly count them. Okay, but how do we practically set this up in our code? Well, we need a way to visit these nodes level by level. We do this using a classic level order traversal. This uses a queue, just a simple first in, first out line, to sweep horizontally across the tree, level by level, left to right. We simply keep track of our leftmost and rightmost index markers for whichever level we happen to be sweeping across. Here is exactly how the mechanics unfold. Normally, you just push a node into your queue, right? But here, we bundle them up. We push the node and its mathematically calculated index into the queue as a pair. As we start processing a new level, the very first index we pull out becomes our leftmost index. From there, as we continue pulling out the remaining nodes for that level, we continuously update a rightmost index variable. By the time the level ends, that variable is perfectly parked on the very last node of the row. Then, at the very end of every single level, we run our simple subtraction formula. We calculate that level's width, and then we check it against a running tally. Let's call it max width. If the level we just finished is wider than our previous record, we update max width. We repeat this for the whole tree, and that guarantees that by the time we run out of nodes, we have definitively found the widest level overall. Now let's talk efficiency, because that is what separates a good solution from a truly great one in an interview setting.
Looking at our complexity analysis, our time complexity is beautifully optimized at O of n, where n is the total number of nodes in our tree. Why? Because our level order traversal queue ensures we are processing each of the n nodes exactly one time. No backtracking, no redundant calculations, just a single, extremely clean sweep. And for space complexity, that's also a solid O of n. This is governed entirely by the queue we're using during the traversal. The queue grows and shrinks, sure, but we have to plan for the worst-case scenario. In a fully populated binary tree, the very bottom level holds roughly half of all the nodes in the entire tree. So, at its absolute fullest, our queue holds approximately n divided by 2 nodes, which drops the constant and simplifies to a fantastic O of n space complexity. So look at what we did here. We took a chaotic, hard-to-measure binary tree filled with invisible null nodes, and by applying a simple mathematical formula, we forced it to behave like a highly predictable array. This approach isn't just a clever trick for this specific problem. It's a real game changer. It's a foundational shift in how you can manipulate data structures. So I'll leave you with this. What other seemingly impossible tree problems could this indexing mindset instantly solve for you? Think about it.